Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
And there are lots of different recommendation algorithms. So part of this work is to try to understand how much these algorithms are vulnerable to rogue users who may come in to the systems and enter profiles for the purpose of affecting the system behavior in some way, maybe to their advantage, for instance. And these rogue agents could be users and real users that may be authors of books, for example, or people who want to push or maybe reduce the ratings for particular items. Or they could be agents, the automated agents that are designed to come in and affect the behavior of the system in some way. So I want to talk a little bit about vulnerabilities of collaborative recommendations in general, talk about the type of attacks and some examples of attacks that can be made against systems. Give you a little bit of background and summary on some of the work that's been done in this area, and there hasn't been a lot of it, so this is relatively new stuff. And part of our work has focused on, in fact, understanding or building a more formal framework for different types of attack models. And these attack models are the kinds of attacks that the profiles that can be injected into the system in order to bias the behavior. And these include things like what we call average attack, bandwagon effect attacks, and some interesting results on attacks that are focused on segments of users. And I'll also talk about nuke attacks, which is most of these other kinds of attacks people have talked about are designed to push some particular item, for instance. I'll talk about nuke attacks as well, and some results there where the attacks are designed to maybe reduce the ratings for a particular item. I'll talk about some possible solutions. We've had some very good results in certain type of hybrid algorithms that seem to be much more robust against these kinds of attacks. And I'll also talk about part of the motivation behind understanding these models, attack models, is to be able to then detect them and respond to the attacks within the system. So those are some of the elements that I'll talk about. Let me give you a quick example of collaborative filtering, since our work is focused essentially on standard collaborative filtering right now. I think probably most people here are familiar with standard user-based type of k-nearest neighbor approach for collaborative filtering. You would have a database of ratings, generally speaking, for items. Items can be movies or products or books or kinds of things that are often recommended in e-commerce type of systems. And standard collaborative filtering, user-based collaborative filtering, works by trying to match the profile of a new user, let's say Alice in this case, who has come and rated some items, maybe as part of her profile from past behavior. And then the recommender systems tries to recommend or predict the rating of Alice on some other item that she has not purchased or has not seen yet. Item 6 in this case, in this particular example. Normally, in user-based collaborative filtering, the idea is to find the most similar users to Alice, and then based on those similar users, or the k-nearest neighbors, try to do a recommendation. So if I use just simple correlation between Alice, the things that she has rated, and the other users in the system, and I just want to find the best neighbor, in this case, ends up being user number 3 with 0.9 correlation. And based on that, then I might be able to predict that Alice is most likely going to rate item 6 very low, and therefore item 6 should not be recommended. But of course, most recommender systems try to look for items that should be recommended to a particular user. So obviously, this whole process depends on these profiles that have been entered into the systems by these previous users. And by the way, I'm using ratings in here, but collaborative filtering systems can also work not necessarily based on explicit ratings. It's possible to look at implicit ways of determining notions of some measure of interest of users on particular items, like purchasing things, such as maybe in the case of clickstream data, by viewing pages and so on. So the type of attacks that we are focused on are what we call profile injection attacks. Basically, they consist of a number of attack profiles that are entered into the system, and they're engineered to bias the system's recommendations in some way. In some past work, this has been called shilling, or shilling attacks. I tend to use the term or the phrase profile injection attacks because shilling, the idea is not just necessarily to push an item, although most of the work has been focused on pushing some particular item, but it could also be used to do other kinds of attacks. Push attacks in general are designed to promote an item, as I mentioned before. And the typical type of a push attack, and I'll talk about different kinds of push attacks, but the typical kind usually gives a high rating to the item that's being pushed and includes some additional ratings for other items in the database. And the distribution of the ratings on the other items really determine the type of attack model. But there are other types of attacks. So Nuke Attacks I mentioned, which is designed to maybe get certain item to be recommended less frequently. Or system-wide attacks that may be mounted against the system just for the purpose of degrading the performance of the system or accuracy of the system. Yes?
So does Amazon have a role problem with it?
Amazon, let me postpone answering that question for a couple of minutes here. So here's a successful push attack, just based on the previous example I was just showing you. So in the previous example, we only had users 1 through 7, which are real users in the database. And Alice was, the most similar user to Alice was user 3. And therefore, item 6 would not be recommended to Alice because the predicted rating was very low. But suppose that we inject attacks 1, 2, and 3, the 3 profiles down at the bottom, which, as you can see, are given ratings for some of the other items in the database that seem to be kind of average ratings, but very high rating for item 6. And as a result of this, now I have attack 3 profile being the most similar profile to Alice. So if I use the same kind of approach I was using before, I would end up with the best match being 0.93 in terms of correlation with Alice, and therefore Alice is now going to be recommended item 6. So even that single attack, or by injecting these 3 attacks, which change the correlations, I was able to affect the system. Of course, this is kind of a toy example, but it shows you what kind of a problem we are dealing with. Now, this is a user-based algorithm. User-based collaborative filtering, user-based k-nearest neighbor, which is probably the most standard kind of collaborative filtering system out there, is based on comparing similarities of users. So profile of a current user, for example, with other users, and the k-nearest neighbors would be the k-nearest, the top neighbors, most similar users, in this case to Alice. There's another form of collaborative filtering called item-based collaborative filtering. It's been successful, and you were asking about Amazon.com. Amazon.com uses item-based collaborative filtering. And the reason they use item-based collaborative filtering is because in terms of the main purpose of it is scalability. User-based collaborative filtering, in real time, you have to compare these users with Alice, for instance. You're talking about millions of users, possibly tens of thousands of items, and this is not very practical. Item-based collaborative filtering uses the same kind of data, but the objective is to look at similarity of items. So if I'm interested in giving a recommendation for item 6 to Alice, let's say, I would compute the similarity of item 6 in terms of rating, so the columns in this case, with all of the other items. And then I would look for some other item based on that similarity, the most similar item that Alice has rated before, and the chances are Alice would be rating this item 6 in a similar way. So the nice thing of the reason this is more scalable because this computational similarity among items can be done offline. It doesn't have to be in real time. So just to show you an example, the best match in this case to item 6 would be item 2. And I've computed item similarities using, in this case, some variation on cosine similarity measure. And of course, the similarity is not based on semantic information. It's just simply based on the ratings that people have given, other people have given to these items. So therefore, the prediction would be 2 for Alice's rating on item 6, because Alice has rated this item, which is the most similar item to item 6, as a 2. Now, item-based collaborative filtering also is vulnerable to these kinds of attacks. But it turns out, as I will explain later, item-based collaborative filtering is much more robust against the kind of push attacks I was just describing. So part of our work has been, and in fact, the previous work that's been done in this area has been has concluded that item-based collaborative filtering is sort of the answer to the problem, because it's very robust against the kind of attacks that have been suggested in the past. So part of our work has been to disprove that. In fact, we have designed some attack models that are very successful against item-based collaborative filtering. So that kind of gets back to answer to your question. Amazon.com would be vulnerable to certain types of attack models that I'll be describing today. So here is an attack against this item-based collaborative filtering. I've added, again, 3 attacks at the bottom. And now you can see that item similarities shows that the best match is item 1, not item 2, as a result of recomputing the similarities after the attacks. And therefore, the rating, the prediction for Alice on item 6 is going to be 5. Now, the way this worked is that, we'll go back to this previous slide in here, is to some extent the way this attack that I just showed you in that example was designed was based on the knowledge that item 1 is relatively popular. Lots of people have rated it. Okay, not necessarily rated it highly, but the fact that lots of people have rated it. If I know that somehow, then I can design my attack so that it would be effective against this item-based collaborative filtering. In fact, that's sort of the motivation behind one of these attack models I'll describe a bit later. How would I know that? Well, it's not too hard to figure this out in most systems. For example, if it's a movie rating, right? You know, I don't have to have access to Amazon.com or, let's say, Movie Lens data or any other kind of internal database to be able to say, for example, that, let's say, Star Wars is a very frequently rated movie, right? Or maybe Return of Jedi, or some of these blockbuster movies. You can probably do some similar things with books and products and so on. So some of the previous work that's been done in this area, some work in 2004 by O'Mahony and others, worked mainly on the theoretical basis of this kind of vulnerability. In particular, they looked at the upper bound on prediction shift. And by prediction shift, I mean the prediction of a system on an item before and after an attack, you know, how much shift there is. And that assumed, this model, that the theoretical model assumed that the attacker would have full knowledge of the data distribution, which is, of course, not practical. Lamb and Riddle in University of Minnesota, the Group Lens project, they also did some work in here, and they did some empirical studies on simple attack models. And, in fact, that was the work I was describing earlier, where they looked at the item-based versus the user-based on some simple attack models. In fact, the attack model that they designed was called average attack, which I'll describe in more detail. But that also assumed that the attacker would have extensive knowledge of the database. In particular, the average attack, which was the most successful attack that they described, assumes that the attacker knows the average and the standard deviation of ratings on each individual item in the database, all of the items, and which is, again, not very practical. So those are the general conclusions. Substantial vulnerabilities exist. User-based algorithms are particularly vulnerable against some attacks.
So one question.
Yes.
It seems like on Amazon, they actually tell you what the average rating is.
Yes.
They don't necessarily tell you computable by just looking at a sampling of the...
It is possible, yeah.
So in some scenarios... So do you have any other criticism of that work? Other than the
Well, the question of practicality is two questions. One is the degree of attacker knowledge required to mount the attack successfully. The second thing is the effort required. So to find the average user rating, for example, on all of the items in the database is still not very practical. I mean, it's possible to do, but it would be very difficult to do. So average attack is not an impossible attack to mount. It's not a theoretical impossibility, but it's just in terms of practical application would be difficult to do. But also, you're right. I mean, one lesson maybe from this is that maybe the average item rating should not be published in general. Maybe in some other way, maybe should be obfuscated in some way when people publish it. Yes.
Does Amazon even use those scale ratings for their recommendations?
They do. They do.
The recommendations based on just what people buy, so it's a binary.
Amazon.com gives different kinds of recommendations. They give recommendations based on association rule analysis or simple correlation analysis. That's the kind of thing you get when you, for example, click on an item that says people who bought this also bought this.
Right.
So that's a sort of a model-based algorithm for giving recommendations. But their standard recommendation algorithm, the recommendations you get when you are a registered user or when you go in and after you purchase things, or if you rate things, those recommendations are based on this item-based collaborative filtering. So it's based on the ratings people have given to various items. Usually this like a 4-star or 5-star rating, 1 to 5, similar to what I was describing. However, if you as a new user go and purchase some item, that's also taken sort of as an implicit indication that you're interested in an item. I don't know how they translate the rating into stars, but that is taken as a high rating for some particular item. I don't believe they actually add that to their database as a profile. But they do use that in order to match your profile with profiles of other people in the database who have rated things. So lots of work has been done on trying to translate between implicit indications of interest like purchasing or some other indications, translating that somehow to kind of a rating scale. So I'm not completely sure exactly what they're doing with that. Yes? If you're asking me what attackers are doing to gather information, I don't know. But it is possible, yes. I mean, it is certainly possible to do this kind of exploration of systems, because these are open systems, to try to, for example, add profiles or add things and see, or just, for example, try to determine what is the correlations that the system gives you between the items. Just by clicking on some item, you may get a recommendation. So you would know, what are the similar items, for example, or what are the correlated items. So that information could be useful. We haven't, in this work, we haven't really tried to explicitly use that. So we have focused on how we can make these attacks, very practical attacks with very limited knowledge that can affect the system as a whole for pushing items, for instance. So I'll describe some more of that in a little bit more detail. Let me tell you, in fact, what are the specific questions that we have tried to focus on. One is the question of practicality. So as I said, previous work assumes lots of system-specific knowledge that the attacker has to know or maybe learn over time through some mechanisms. The idea is, can attacker be successful with a lot less? So part of our focus has been on limited knowledge attacks that require very little amount of knowledge. Secondly, attack models. We want to look at more effective attack models, particularly in the case of item-based collaborative filtering. And specifically, I'll look at this attack called segmented attack, which is very useful against, or very powerful against item-based. And our ultimate motivation is identify different kinds of recommendation algorithms that are robust against these type of attacks. Kind of like item-based algorithm is robust against certain type of attacks. We would like to see algorithms that are robust against all of the attack models that we can design. And there are some indications that hybrid algorithms, certain type of hybrid algorithms, which I'll discuss in more detail, are much more robust without necessarily sacrificing too much accuracy. You can also focus model-based algorithms. Model-based algorithms include algorithms that maybe through machine learning or data mining build models, user models, and then the users are compared to those models and recommendations are generated that way. The generic attack profiles would look something like this, where you have all of the items in the database. One of the items is a target items, let's say IT, all the way to the far left, far right. Then potentially you have three, the rest of the items that are in the database, in the profile, are partitioned into three sets. IS is some sort of selected items that I might select in order to maybe use as a part of the attack profile if I am the attacker. For instance, I selected item 1 in that example I gave you as an item that was very popular or very highly rated. But you could select more. And the deltas, those delta functions in there, represent the ratings that are given to those particular items based on the attack model. The IF is some sort of filler items. Those are some ratings I would give to some additional items. And generally, these ratings might be determined based on some sort of a random distribution. Then there's a whole bunch of other items in the empty, which are not rated in the profile. So previous work that looked at attack profiles assumed that basically there is no individual selected items. So IS was empty. And also IEmpty was empty. So everything else in the profile were filler items. So the only question was, how would that sigma function be defined, which assigns these random ratings to these filler items? And the IT was then rating for push item would be the maximum rating value. So let me say a little bit about a methodological note in terms of some of the results that I'm going to be presenting. For our test data, we used Movie Lens 100K database, which is I guess I think it was close to 1,700 movies of and about 1,000 users approximately. And the data is also designed that all the users in the data have at least 20 ratings, so it's been filtered so that it's a little bit less sparse. For the purpose of testing, we selected, for example, for push movies, we selected 50 different push movies. And these were selected randomly, but so that the distribution in terms of the sparsity of the ratings on these movies kind of mirrored the overall average in the data. Also selected 50 users randomly. And then the results were averaged over all possible pairs of movies and test movies and test users. We generally use K equals 20 in the experiments for K nearest neighbor, either item-based or user-based. And in evaluating results, we use two different metrics. One was the prediction shift, which basically shows how much the rating of a pushed movie or item would differ before the attack or after the attack. And this is useful, but it doesn't tell the whole picture. And the reason is that what if the result of the attack is that the prediction would shift for all of the movies. So that doesn't necessarily mean that the movie, in terms of ranking, would be recommended more highly than other movies or items. So we wanted to also look at some other metric, and in this case, we looked at hit ratio. And the hit ratio measures how often the push movie, would actually appear in the top N recommendations. So we look at the top N recommendations, I mean, we can plot this against N, and show how often the movie would actually end up in the recommendation set if you take the top ranking recommendations. So both of those together would give us a much better picture. So let me talk a little bit about attack models. I talked about the average attack, which was designed, which discussed earlier in Lamb and Riddle. They assume that attack profile consists of the push item plus rating for all of the other n items in the database. And all of those n ratings, so those were all the filler items. All of those n ratings were drawn from the distribution defined by the average rating for each movie. So that means the attacker, as I described earlier, would need to know the averages and deviations for all items in the profile, because the ratings assigned to these items in the fillers would be some random number, basically random rating that's around the average. So it would look something like this. We look at a more general version of the average attack where not all of the n items are rated. So we have this IF, which is our filler set, and those are the random ratings for L filler items drawn from the distribution of these items in that set. But there is the rest of the items in the profile that are not rated. And IT, the target item, is rated as maximum in the push case. By the way, you can change that to a Nuke Attack by changing R max to R min. So, for example, giving it a rating of 1. It's possible to use any of these attacks, both as push and Nuke Attacks. But as I will describe later, in fact, things that are successful as push attacks, attack models that are successful as push attacks, are not necessarily successful as Nuke Attacks for their variation. So the reason we wanted to focus on filler items is, again, this question of practicality. So the most practical attacks are the ones that require the least amount of knowledge and the least amount of effort in assigning ratings. So part of the question, for example, was, can an average attack be still successful if the attacker only needs to give ratings to a much smaller group of items, let's say just 10% of the items or 3% of the items rather than all of the n items? Yes?
When I'm comparing the similarity between two vectors, do I just use the dimensions on which they both are non-null?
Yes.
And then there's some sort of trade-off between, if one vector has a lot of value, then it's going to be closer to another one that has a lot of value than one that has a single value.
Yeah, to some extent that depends on the similarity measure, but all of the similarity measure we talk about in here, both user-based and item-based, you only look at the items that have been commonly rated by both users. Or in case of items, you look at just the ones that they both have values. This is, by the way, it points to a big problem in some collaborative filtering systems, which is the sparsity. Most users, are very unlikely to have rated more than just a few items. So in fact, in many cases, the sparsity results in not being able to make very good predictions. And also, it results in some cases, in fact, not being able to make any predictions at all, because the data is just not there. So that's a potential problem. Okay, so these are some results that you'll see that compare. On the left, you see a comparison for the average attack of user-based and item-based algorithm. And this is, on the left, you just see the prediction shift comparison for the average attack. And this is plotted against attack size. Attack size is the number of attack profiles that are added to the system. So you can see that it kind of plateaus based on the attack size. So I don't necessarily need to give a very large attack size. In fact, in this case, at about 3%, 3 to 4%, I reach the maximum. 3 to 4%, of course, could still be a very large attack, so it may not be necessarily possible to do it manually. An automated agent might do it. We, in fact, looked at a lot of attacks. Most of our experiments, a lot of our recent experiments have been focused on like 1% attack or even smaller. But what you can see in here is that this is, by the way, the prediction shift, the prediction in the movie lens data set, the ratings are between 1 and 5. So in the user-based case, I'm getting a prediction shift of 1.6. That's quite dramatic. But you can see that in the item-based case, I get a much lower prediction shift. So this kind of confirmed those previous results that item-based is more robust against this average attack.
So do you have any idea what the variance is across items? So you might be pushing a certain item.
Yeah.
And it might be harder to push some items than others. Yeah, so do you have any idea?
It is. I mean, our results show that, of course, it's much easier to push items that have much sparser rating, right? So, for example, it's much harder to push Star Wars than it is, and in most cases, it makes no difference to push Star Wars, of course, right? But let's say if you wanted to nuke, it would be much harder to nuke Star Wars than some movie that is much less frequently rated. For our testing, we average over a lot of different movies, and when we picked these movies, we did look at the variance, and we picked movies that have, in terms of ratings, have the variances are mirror the overall distribution in the data, the average. So we wanted to pick movies that generally representative of the average. But we have not done enough experience on specific type of movies based on variance yet, except for what I just described.
So, it looks like, I know you're going to get to some why there are attacks on the item base, but, it looks like item base is working great. Are there problems with item base? How good a predictor is it versus user base? And does it have a lower variance than user base, right? Could it be just that, the item base tends to be closer to something overall, and that's why it's hard to shift?
No, I think it doesn't have a smaller variance. I mean, depends on. I mean, you're talking about in that case variances between the columns in here,
Yeah,
not
so
the.
if we were to look at just in general, if we were to look at the predictions of item base, all the predictions of item, I can tell you something that's very robust to attack, fighter measure, right?
Yeah.
Give everything a rating of 3 or 2 or whatever, some constant, and now nothing gets any shift. But there's some problems with that.
Yeah.
So I'm wondering if item base has any of those problems, right? Does it either A, have a smaller variance, or is it B, a worse predictor in general?
It's not a worse predictor in general. The experiments that have been done on comparing item-based and user-based suggest that in some data sets, like the movie lens data, for example, the prediction accuracies are similar to user-based algorithms. In some other data sets, like clickstream-based database, they varied. So I don't know if there is a conclusive evidence one way or the other.
So that's, there's nothing obviously wrong with it.
No.
So in this database, for example, are there that many users that have rated, say, 1%, 9% of all the users in the database? And how realistic is it that I won't be able to tell the attack from the user and you can have 10% of the users?
Well, I'll discuss that in a little bit later on, but we looked at attacks across lots of different filler sizes, and I haven't described that yet, but in fact I will in just a second. It shows that especially in some of the attack models we've been looking at, the attacker is only required to provide ratings for very few items. But yeah, the data set also was designed that each user has rated at least 20 movies. So that's of course not quite that large, but then you also have users that have rated quite a lot more movies. Question?
It seems that the time when people attack is like when a new book comes out and you want to talk to your competitor and you want to screw
Yeah.
a book. So in that case, you're kind of automatically in the doesn't have to make
Yeah. So I mean that's an interesting question, and we are looking at that as part of our detection methods. Part of our detection method is, well, there are two questions. I mean, I'm kind of jumping the gun in here, but just to answer your question, one is, can we identify attack profiles? So that's sort of a classification problem. The other problem is, can we identify items that are at some point under attack? And the method we are using for that is more sort of a time series problem where we look at the sparsity of rating and distribution and frequency of ratings on particular items. And that's a difficult problem. It's not as simple as it seems because there are lots of things in the life of, let's say, a movie that might cause these things to change. like when the movie comes out on video, for instance, or some other thing. Also, some movies are very different. So we are looking right now for this particular data set at how these movies are distributed, and if you can kind of segment and see, let's say cult classics, for example, have a different type of a distribution than, let's say, some other type of movie that is a blockbuster and then just kind of dies out. So, I mean, those are interesting problems. We haven't looked at all of those things, but we are just having some preliminary results with detection, which I'll describe. I should say, probably up to this point, our work is much more useful for attackers than it is for preventing the attacks. But you have to kind of model these attacks in order to be able to prevent them later. So one type of attack model that we looked at is bandwagon attack. And the idea is that if the system's rating distribution overall is unknown, but if I can use some domain knowledge to identify some products or items that are very frequently rated, like I was describing earlier, then I can associate the pushed item with these items. So kind of bandwagon effect, right? And there is minimal system-specific information required in this case. It is possible to identify these items externally, and, for example, blockbuster movies. And here is our model for bandwagon attack. The basic idea is that I would select some set of items, and those would be selected based on some external knowledge, and these would be highly or frequently rated items. I still would have my filler items, but the filler items would be given only random ratings distributed over the whole database. So I don't need to know the average for each of those items in the filler size. All I need to know is what is the average rating overall for the whole system, or just guess it, because it has to be just close to that. For example, in Amazon.com, it's close to 3.6, right? And this is a well-known thing. And then I have the unrated items, and the rated item would be the target item. The target item would be given the maximum rating. So the low knowledge requirement comes from the fact that random ratings for filler items are centered on overall system average rather than individual items. And frequently rated items can be guessed or obtained externally. So here are some results. We used the small profile size. By profile size, I mean the number of filler items, essentially, the percentage of filler items. But here is a comparison in terms of prediction shift for user-based algorithm. The average attack, a 10% average attack, which would be very large, compared to a 6% bandwagon attack, and they got similar results. And even in terms of hit ratio, you can see that average attack and bandwagon attack are pretty close. And this, in this case, is compared to the baseline, which is no attack, right, for those same sort of movies. So what this shows is that using a much more limited knowledge attack model than average attack, I was able to get essentially the same results against user-based algorithm, or some similar results. Yes?
Can you remind me what a hit ratio of 0.6 is?
Hit ratio of 0.6, that means that, so for example, this is the number of recommendations. So if the system produces, let's say, 20 recommendations, in this case, I'm getting over 0.8. That means I'm getting 80% hit rate. So in 80% of the cases, the one that the item that would actually be recommended is the correct item that the user will look at.
So the fact
So,
that the baseline is going up means that the item being promoted was actually a reasonably popular item.
well,
Included in some of the
you have to be a little bit careful about this. I mean, hit ratio, obviously, the larger the number of items you recommend, the larger the hit ratio is going to be. In fact, if I recommend all of the, in this case, 1,700 items, hit ratio would be 100%, right? So we are particularly interested in hit ratio over smaller numbers in here because we want to be able to recommend. That means more accuracy. If I recommend only 10 items out of the 1,700, right, and I get, let's say, 80% accuracy among those, that's pretty good, right? And we are getting relatively good results.
You give me the intuition is it that it is able?
These are user-based. So we are looking at users, and also it's averaging over a number of movies. And I'm pretty sure that Star Wars was not one of the test movies, and because although we picked our test movies at random from among the 1,700, we picked movies that kind of their distribution in terms of ratings centers around the average, which Star Wars is not one of those. So this probably is more typical of an average movie rather than something like Star Wars. Now, this is an interesting experiment that we looked at the percentage of the filler items that are necessary in order to achieve good prediction shifts. And this is Bandwagon Attack, that's average attack. You can see, and this is both user-based algorithm. And you can see that in both cases, in fact, there's a point of diminishing return. So if the attacker filled in all of the, give ratings to all of the other items, in fact, the prediction shift goes down. The best results are achieved at about 3%, somewhere between 3 and 7%, depending on the algorithm. So I can only fill in a very small number of the items, or give ratings to a very small number of items, leave the rest empty, non-rated, and achieve the best effect in the user-based case. In the item-based case, I don't know if I actually have a result in here. In the item-based case, you don't see this drop. What you see is a continuous growth, but it's a logarithmic behavior. So you still achieve near maximum at about 7% or so in most of the, at least in the case of the average for item base. So still, you can achieve, the attacker can achieve the best or near the best results by just assigning a few of the filler items ratings. Okay, let me talk about segmented attack a bit. So far, in all of these attack models we looked at, there's an equal value assumption that a recommendation to any user is equally valuable to the attacker. And this is not likely to be true in general or in real life, because what's more likely is that recommendations to certain group of users or certain users are much more valuable. And for example, the idea of maybe recommending things to likely buyers, right? It's the same idea of target marketing, right? So it's much more likely that if you target or try to recommend or try to push some particular item to a specific group of users that are most likely to act on that, this would be a lot more effective. So the segmented attack assumes that attacker wants to push a product to a target segment of users. And those segments of users are those that have some preference for similar products or items. So the idea is attack users who share particular preferences. For instance, example in the movie context is, let's say, all the fans of Harrison Ford movies or fans of horror movies. The question is, how would I know that some segment of users are fans of Harrison Ford movies? Well, if I want to design an attack, I don't actually need to know that, right? All I need to know is that I want to attack fans of Harrison Ford movies, so all I have to do is give high ratings to Harrison Ford movies along with the item that I'm trying to push. So this way, in effect, I'm targeting the fans of Harrison Ford movies because my people that are going to be matched with, with my profiles that I'm adding would be those fans. And this also works in the item-based case. Because I am actually looking at specific items, I'm in fact increasing the similarity of these particular items to the items that I'm trying to push. So it's similar to Bandwagon, but focuses on some notion of semantic similarity in the sense that items are semantically similar in the sense that they're, the same kind of characteristics, for instance. Here's the profile for segment attack. Similar to Bandwagon, but the selected items are ratings for k-favorite items in the database for the user segments. So those selected items are selected in such a way to target a particular segment of users. The ratings for filler items is the same way. They're just assigned randomly, and the non-rated items and are max for the target item. So the idea is to minimize the similarity between target item and non-segment items and maximize the similarity between target item and segment items. And for this reason, it's designed to attack item-based collaborative filtering because you're trying to do this max the similarities. Here are some results. We use the segments of people who used high ratings for 4 Harrison Ford movies. Star Wars, Return of the Jedi, Indiana Jones, Raiders of the Lost Ark, and so on. Of course, these were probably not a very good selection because these are also very highly popular movies, regardless of Harrison Ford. But you can see that this is a comparison of both user-based and item-based. Item-based, of course, is less vulnerable to all of these attacks, except when you are looking at, in this case, well, the two things I'm comparing in here is this is the result of the attack on the segmented target, so the fans of Harrison Ford movies. This is a result of attack on all users, right? And when we compare in here, you can see that there is a huge jump in the case of item-based when you focus on those users. There is also a jump. This turns out that this attack model actually works also well against user-based, but not quite as well as bandwagon and average attack. But it is more successful than the other attack models against item-based. Yeah.
The other slide you have, you're trying to minimize the similarity between non-segmented people and the attack.
Right.
And it seems to fail to do that.
Right. No, because I mean, the comparison of this and this, right, shows that I was able to increase the hit ratio, right? This is just the hit ratio. It shows that I was able to increase the hit ratio when I just focus on those segments of users compared to when I look at all of these.
The missing bar is the non-segmented, I'm sorry, the segmented non-targeted.
That's right.
And hopefully it's like the attack.
Well, the pre-attack is just, without doing adding any attack profiles. That's the hit ratio you're getting on these particular test movies. This is, of course, as I said, this particular test data was not very typical. We tried, let me just show you this. We tried a segment of horror movies. So we picked the top 5 horror movies from some internet website that, has ranked these things. So we did it completely independently. And used a 1% attack against horror movie segment. So here is a prediction shift, here is a hit ratio. Let's look at the prediction shift first. So against the attack size. And you can see a comparison between in-segment users, those that actually like horror movies, versus all users. And there's a big difference between the prediction shift. And in the case of hit ratio also, we end up achieving almost 50% hit ratio, which is difficult to do in item-based algorithms because it's more robust in general compared to all users. And here's the no attack baseline for the hit ratio. So it's still a big difference there. And here is the results on user-based. Shows you that we also get good results in the case of user-based for segmented attack. And in fact, in the case of user-based, the segment attack also works pretty well, even though we are targeting a specific segment against all users, but not quite as well. In the case of Harrison Ford movie, of course, you would expect that because those were movies that in general people like. So that's not uncommon. Let me say a little bit about Nuke Attacks. The idea of Nuke Attack, one of these Nuke Attack models that we designed was what we call love-hate attack. The reason is that you give maximum rating to some set of filler items and then minimum rating to the target item. So it kind of models somebody who really loves some movies and then really hates these other movies, or the target movie. And you can also use variations of this as a push attack. But this is very reduced knowledge because you're essentially using no system-specific knowledge. All you're doing is just randomly assigning maximum rating to some movies, and then the target movie would be minimum rating. And it turns out that, in fact, as a Nuke attack, this ends up being very, very successful against user-based. I'll talk about the results. But another type of attack we designed is reverse bandwagon attack, which is a variation of bandwagon. You take selected items, and those that are rated poorly by many users, and then assign low ratings together with the target items to those selected items. So that means that you're trying to associate selected items with widely disliked items. Now, this is, of course, a more difficult problem than in the push case. And the reason is that the distribution of ratings, the frequency of ratings on items that are disliked is much lower than items that are liked. People are much more likely to rate things that they like than rate things that they dislike. So it's a more challenging problem. But it's designed to reduce the knowledge required because the attacker using this model would select some items that are widely known for having poor ratings. I don't know, what was that movie, Geely or something like that, which everybody seemed to dislike, or there have been some movies like this. And there have certainly been items like this or books like this, but they're harder to come by. So here are some results, and this is just for Nuke attacks. So when I talk about average and random and bandwagon, for example, that just means that I use the same attack model I described, except we replace the R max with R min, right? So use the Nuke version of that. And compare those to love-hate attack, which I just grabbed, and this reverse bandwagon. And on the left is the user-based results, on the right is item-based results. And the interesting thing is that in the case of user-based, you can see that, for example, average attack, which was very successful against one of the most successful, and also the bandwagon, the most successful against for pushing items, are not quite as successful as the love-hate. Love-hate, which is much simpler, in fact, is much more successful for nuking these items in the user-based algorithm. Even more interesting results in the item-based case, because as you can see, for instance, the some of these other attacks that were very successful for nuking in the user-based case are not very successful in here at all. In fact, the most successful ones are still the average, the nuke version of average for item-based, and the reverse bandwagon, which is much less knowledge intensive for the attacker. This is also an interesting result because average was not very successful for pushing an item in the case of item-based. So there are some interesting results that show that, in fact, pushing an item is a very different kind of a thing than nuking an item. Yes?
It's kind of interesting because you're talking about the amount of knowledge that these attacks use, but it seems like there's another factor which is important, which is how detectable the attacks are. So the love-hate seems like it'd be very detectable.
Yeah.
It's so extreme. But the bandwagon would be hard to detect, right? Because you're just acting on probabilities of soul.
That's right.
Did you guys consider that? Like, are you going to talk about that?
I'll talk a little bit about that. And yes, you're right. And in fact, we are working on what we call a utility model for attacks, which we want to develop a utility function, which from perspective of the attacker, the utility of attack is not just in terms of the prediction shift and so on, but also takes into account the cost of the attack. It also takes into account, for example, the cost in terms of the probability of detection of attack. So by trying to build a utility-based model, I think we can do more interesting comparisons.
So now prediction shift of -0.8 isn't really that's not too bad, right? Because you're moving it down 1.
Down 1.
Oh,
yeah. So if you're looking at 1 to 5, it potentially changes it by maybe 1 unit. Okay, some solutions. Something that's been suggested is the idea of explicit trust calculation, for example. So select peers through a network of trust relationships and so on. And in certain kinds of recommender systems, this might be useful. In the large-scale recommender systems, like the ones based on collaborative filtering we're describing, it's probably not very achievable. And the reason is that you need lots of ratings, basically, to make collaborative filtering work, the same sparsity problem that I was describing. So, but there is some work in this area, potential work in this area that might be able to address some of the problems. We've been looking at the idea of using hybrid recommendations, and I'll talk about that. And also, we wanted to look at a little bit at detection and response. Let me talk about this particular hybrid algorithm that we've been using. We use an extension of item-based algorithm. In the item-based case, if you recall, the system was based on comparing similarity of items, but this similarity of items was measured in terms of the ratings people have given to these items. So what would happen if we have a combined similarity measure, which not only measures similarity of items in terms of ratings, the rating similarity, but in terms of semantics of these items. So if there are pages, for example, would be based on content similarity. There are movies, maybe based on attributes of movies. If there are products, maybe based on attributes of products, relational attributes, and so on. So basically, a combined similarity measure in this case, we would use is just a linear combination. We would use alpha, which measures the degree to which rating similarity is used versus semantic similarity. If I use alpha equals 0, for example, that means only semantic similarity would be used. So essentially, the recommender system becomes a content-based type of a recommender system. No collaborative information is used. If I use alpha equals 1, then only collaborative information is used. In fact, the system becomes just the item-based collaborative system that I was just describing earlier. The idea was, first of all, what would be the right alpha to pick, right? And secondly, would that, by incorporating some semantic information, would that impact, would it make it less likely that the attacks be able to be successful against the systems? So here are some results. On the left, you see the impact of alpha on mean absolute error. So the lower, the better, of course, in that case, right? So in fact, we can see that the best result is not obtained by just pure semantic or pure collaborative, but by a combination. In this case, for this data set, it's something around 0.4. We've tried this on lots of different kinds of data sets, including clickstream data sets with just page content, for example, keywords, and so on. And you still get some similar impact, not necessarily with the same alpha. But, so I get pretty good accuracy, in fact, better accuracy than just the pure item-based collaborative algorithm if I use this combination. And for that particular combination, 0.4, I've shown you on the right the hit ratio of the hybrid model versus just the item-based. And this is for the horror segment, so the segmented attack. Because segmented attacks was more successful against the item-based, so we wanted to compare the results. Yes.
So it seems like if I was trying to promote something on floor reviewers, so positive thing, then the item promoting would be, say, a very poorly written, or very poorly produced for. If that was the case, wouldn't it be able to score well on the semantic matching?
Yeah, it's possible. I mean, we haven't really tried to. I mean, you could. It's conceivable that you could design attacks that would be able to design attack models that would be able to work against also the semantic aspect. And in fact, we are working on those. But based on the standard attack models that we were describing, it seems like a combination of these things would be much more robust. And you can also argue that it would be much more difficult for an attacker to design an attack without explicit knowledge.
My goal was to maximize sales of my really bad horror book.
Yeah.
Then, we match semantically, and as you mentioned before, I want to get people who are most likely to buy a horror book anyway. So they'd be the ones I go after. Or would be the other horror books that I'd be rating if I did an association.
It's possible. Our data, this particular data set, we did use the horror segment, so we did pick the top 5 horror movies. And at least for those movies that we tested, that doesn't seem to suggest that. But certainly it's conceivable that for a particular book, something like that would be the case, especially depending on what kind of similarity you get for the semantic aspect.
Wait, is this the ratio of the 50 movies or of the 5 horror?
This is the hit ratio on all possible combinations of the 5 horror movies. So taking 1, 2, 3, 4, or all 5s, and then in each case picking the users that rated all of these combinations highly. I think we gave 5 to those movies, and picking those as the users. So this is on the 5, and then testing the results on the 50 test movies.
So the results, the test results, the value of the hit ratio is on the 50.
That's right. It's on the 50, but it's on the
It's for the segment.
for this. That's right. For the segment of users that like those 5
You
movies.
measured the hit ratio of the 50.
That's right. All of those results are over this randomly selected 50 movies that we have. Okay. For detection, let me just kind of end with some. As I said, these are kind of fairly preliminary. But the basic approach right now we are taking, well, there are 2 approaches. One is the classification approach to try to identify the attack profiles. And the other is the idea of being able to determine potentially what items are under attack or maybe under attack. And right now, the only results that I can talk about with a little bit more certainty is that classifications we seem to have found some good combination of features for classification that seem to work quite effectively in identifying at least the average and random attack models. And we haven't tried things with bandwagon or segmented attack, but there are some generic attributes. For example, one of them is called rating deviation from mean agreement, or RDMA. And this measure multiplies the average difference in user ratings from the mean rating on each item in the profile. And actually, it multiplies it by the inverse rating frequency. And the reason for incorporating inverse rating frequency because of the problem we were describing earlier, if the movie has a very high frequency in ratings, it's very likely that it's not very vulnerable to attacks. So by looking at only inverse rating frequency, we zone in on movies that are most vulnerable to attacks. Sort of like TF-IDF, using TF-IDF in the context of text processing. Another feature is average correlation of the profile's k nearest neighbors. So looking at a particular profile that we want to classify, we want to measure the average of the most nearest, the k nearest neighbor for some k. I think we use k equals 10 in this case. Variance in the number of ratings by the suspect users compared to the average number of ratings per user. And for the filler section in the profile, we looked at the filler mean variance. In other words, the user's average rating variance from the mean rating of all items in that IF, the filler items. That might tell us something, for example, that's useful for identifying this average attack, because in the average attack, the ratings for the filler items by the attacker are generally very close to the the average for individual items in the whole data. If you see a bigger variance, then it's more likely that it's, or if you see a very low variance or variance very close to the average, that might be an indication, for example, that it's an attack. It's an average attack. Also, we looked at filler mean difference, absolute value of users' mean rating over IF minus the system's mean rating over IF. This would be more useful for a more random type of identifying more random type of attack. We have included some additional things. We are experimenting with different kinds of features, but the set of features currently we are using, we are getting actually very good results. For example, C4.5 classification on an average push attack of 10%, we are getting up to 90% or more accuracy, depending on the filler size. So it turns out that one of the advantages of having a smaller filler size also is that it makes it harder to detect the attack. If you have larger filler sizes, it makes it easier to detect the attack, as it suggests. Not that much difference if you pick the right features. The best feature seems to be, the most informative feature seems to be that first one, that rating deviation from mean agreement, RDMA. And that's quite effective in identifying quite a few of the attack profiles. And then the other ones give us, the combination of them give us the result that you saw in there. Yes?
I don't know how you've done this one, but it'd be interesting to say, run your classification and just eliminate everybody who's labeled as, bad, and ask the question, is it bad to have both negative, right? If you pull those users out, is the
It does get worse a little bit.
It does.
Yes. So there is going to be a trade-off in doing that. So, I mean, we have done a lot of experiments, which I'm not using in here because we need to verify these results before I can put them in the talk. But what we have so far suggests that there is a small reduction in a small increase in mean absolute error. And interestingly, you see that K&N classification, for example, seems to do better. But in fact, K&N does worse. So if we do classification based on K&N and then remove those attack profiles, then we get more of a drop in accuracy than we do if we do C4.5. I'm not sure exactly why that is the case, but there could be that in general there is a trade-off between accuracy of classification of somehow picking these things or the rate of false negatives and the prediction accuracy. So I don't know. I mean, those are some things that are questions that have to be answered. But there are some seemingly interesting results. And it does seem like, however, classification may be the right approach in trying to at least identify these attack profiles. Now, this is assuming, of course, picking some test movies that are being attacked. It doesn't tell us necessarily what movies are being attacked. So we need to combine this with this idea of I talked about maybe doing some time series analysis to try to determine if some movie at a particular point in time is under attack or not under attack. And if it is under attack, can we, just based on these rating distributions, try to determine what type of attack it is? So identifying the attack profile is one thing. Identifying the movie that's being attacked is yet a different problem. Okay, so to sort of conclude, the idea of collaborative spam, clam maybe, seems to be a much worse problem than people thought might exist. It seems to be very easy to target and achieve the kind of results the attacker might want. Common algorithms such as user-based certainly, but even item-based for certain type of attack models are quite vulnerable. And furthermore, these attacks, successful attacks against these algorithms can be achieved with very limited system knowledge in certain cases. And the reason we want to understand the properties of these attack models, of course, that it can help us design more robust algorithms, such as, for example, this hybrid algorithm that I was describing. And of course, part of the detection mechanism is going to be not just these generic kind of attributes that we look at or features we look at, but perhaps some more specific characteristics of specific attack models that could be incorporated into a general classification process, so that we can have a generic algorithm that could be, for example, incrementally updated based on attack models that come up to identify these attack profiles. Some of them, as you mentioned, are much easier to identify. Like the love-hate attack would be very easy to identify, for example. But there are some other attack models that would be more difficult. The other thing we want to do is, what if the attacker deviates from the standard attack model, make it more fuzzy, right? So think about a love-hate attack, but maybe there is some filler items in there that are kind of fuzzy, right? Or even the average attack, make it more fuzzy. So the chances are that would affect that would have an impact on the effectiveness of the attack, but it would make it harder to detect. So this is why we want to focus on this utility-based model, which incorporates, from the perspective of the attacker, the utility of the attack, both in terms of detection and the cost, and also effectiveness of the attack, for example, in terms of hit ratio. Other kinds of things we are going to look at: clickstream data sets, collaborative recommendations in the context of web usage, web navigation is very different than rating items. So recommender systems, for example, that generate dynamic content based on user clickstream behavior. And that data is very different than this rating data, because you're dealing with, sometimes just binary data, or at least some sort of implicit ratings. And certainly there is no implicit negative ratings. So it makes it so the attacks that can be performed is not based on an attacker going and maybe, for example, injecting a bunch of ratings, but could be based on, for instance, the attacker maybe simulating certain type of behavior on a particular website by an agent. And also text-based data, so like user opinions, things like CNET or other, even Amazon.com, where the user might go in and enter some words or sentences or things that are trying to boost or reduce the popularity of some particular item. So those are some issues that we are trying to address. Okay, so that's it. Any questions? We did. I'm trying to remember. I think at least we did in the case of the push attacks. We tried that. And we got similar results when we, particularly in the case of prediction shift, when you compare to the attack size, we just measure a percentage. So the attack sizes become smaller. The attack sizes become smaller relative to the total size of the database. But our relative results in comparison of these different attack models and algorithms didn't change. But of course, we were reducing the data size from the full data set. So the idea of maybe using a much larger data, we have not done. There is a couple other data sets that we are looking at that might allow us to do that.